Welcome to AEFAC webinar series, What's New in AS 5216. This is our second webinar in this series. This afternoon, we'll be discussing about post-installed rebar and fastenings for redundant non-structural system. A few housekeeping items. For any questions that you may have, please type in the Q&A. Please click the Q&A icon and type your questions there. This session is being recorded and will be made available on the AEFAC website, as well as the PDF slides for today's presentation. You'll also be receiving a follow-up email for feedback, and our next webinar will be discussing about anchor channel. Right. So to start off, I'd like to just highlight again the three critical elements to achieve quality assurance for anchors. The very first one, anchor product must be independently tested and assessed for it to be fit for purpose for its intended application. The second item in the quality assurance framework is the design. So the anchor needs to undergo a robust design to ensure that all potential failure modes have been considered and the design is being done for the critical failure mode. Last but not least, which tend to be the weak link in the quality assurance framework, is proper installation. Many failures have occurred in the past due to poor installation practices. So these are the three critical elements to achieve quality assurance for anchors. Brief introduction into AEFAC. AEFAC was founded in 2012. It is a non-for-profit industry initiative founded by Swinburne and 6 other industry members. As you can see on slide, AEFAC was later joined by 7 other supporting members. So AEFAC was founded to introduce governance to the anchor industry, so based on the three critical elements that was discussed earlier. Prior to the formation of AEFAC, the industry was fragmented and there is no uniformity in terms of anchors prequalification, specification, design, and also installation. AEFAC contributes to various sectors in the industry, including providing guidelines for designers, training for contractors, guidance for field engineers, manufacturers. And at Swinburne, we continue to do a lot of R&D into anchor research. As seen on slide, the best anchor product is only as good as its installation. The AEFAC Installer Certification Program is to train and assess installers' competency in installing post-installed anchors in accordance with manufacturers' installation instructions. This program has been referenced in various Australian standards and also road authority specifications such as Vic Roads Section 680. So AEFAC instigated TS 101 in 2015, which is the first deemed to satisfy design guidelines for fastenings in concrete. TS 101 has since been upgraded to a full Australian standard, AS 5216 in 2018, and the latest revision in 2021 covers additional design scope, namely seismic, anchor channel in 3-directional loading, post-installed rebar, and redundant non-structural connections. So this afternoon, we'll be discussing on post-installed rebar and redundant non-structural connections. The next webinar in this series will be discussing on anchor channel. Oops, I think I moved a bit too fast. Again, as usual, there are many technical publications free for download on the AEFAC website. So for any queries that you may have, please refer to these freely available technical publications for download. Without further ado, I'd like to invite Dr. Tilak Pokharel, the National Technical Manager of AEFAC, to present on post-installed rebar.
Thank you, Jesse. Good afternoon, everyone. As Jesse mentioned, I am Tilak Pokorel, and I am the National Technical Manager for AEFAC. As Jesse mentioned, this webinar is being recorded, and the video will be available on website. And for those who are watching this seminar recorded, and those who are watching this seminar on web version, you might not be able to see some animations and the pointer. I'm sorry for that before I start. In this presentation, I'll be talking about the post-installed reinforcing bar in next 30 minutes or so. I'll start with the basic information of post-installed reinforcing bars and how they are different from other chemical anchors that has been there in AS 5216 2018 version. I will then explain why and how the design method of post-installed reinforcing bar is different from that of chemical anchors, followed by a pre-qualification and design of a post-installed reinforcing bar connections. So I'll be talking about anchor model, rebar model, their similarities and differences. Finally, I will conclude my presentation by providing some guidelines or suggestions on selecting the proper design method or selecting proper design documentation for anchor model and rebar model. Let's start this presentation with the official or the standard definition of post-installed rebars and chemical anchors from Australian standard AS 5216 2021. The standard defines post-installed reinforcing bar as reinforcement that is anchored into mature concrete, which is 28 days old, using adhesives in a drilled hole. Similarly, the standard defines chemical anchors as post-installed fasteners that includes a steel element, and the element could be threaded rod or reinforcing bar, and a bonding compound that transmits load from embedded steel elements into the substrate. There are some overlap, as you can see in the definition, between post-installed reinforcing bar and chemical fasteners. Thus, the design and pre-qualification of those two types of fasteners are sometimes confusing. By the end of this presentation, I hope I will be able to clear some of those confusions. Post-installed reinforcing bar, they are also known as PIR, they are installed when concrete gets matured. So once the concrete is hardened, the right size hole is drilled at required location of required dimension. After the hole is cleaned as per the requirement, the chemical is injected, usually two-thirds of the hole, and then reinforcing bar is inserted. The post-installed reinforcing bar will be able to carry tensile force only if we follow the design philosophy of AS 3600. Now the connecting member, the another concrete member, will be poured on top of the old concrete member, and as the post-installed reinforcing bar doesn't take shear load, all the shear loads has to be taken by the concrete surface. So it is very common to have a rough surface to have better shear transfer between old concrete element and new concrete element. Now let's have a look at some of the common examples of use case scenario of those post-installed rebar connections. The first one is a connection of new slab. This is slab to wall connection. The balcony extension. This is slab to slab connections. The bridge enlargement. To close the openings in the slab or slab extension, the staircase connection to the wall, and wall extension itself. And these are a few more examples of post-installed reinforcing bars to build a new column or to extend existing column, to use them as a misplaced or missing rebars, beam connections, and finally the post-installed reinforcing bar are used as the additional reinforcing bar wherever required. Before looking into the post-installed reinforcing bar in detail, let's have a look at the design of chemical fasteners in tension in accordance with AS 5216. The fasteners needs to be verified for 7 possible failure modes, and this has been explained in chapter 6 of the standard. The possible failure mode for tension is steel failure, concrete cone failure, pull-out failure, combined cone and pull-out failure, splitting failure, blowout failure, and supplementary reinforcement failure if there are any supplementary reinforcement. The concrete blowout failure is only possible for undercut anchor or headed anchors. So we will have 6 capacities associated with each failure modes, and the smallest would be the design resistance of the fasteners. If there is no supplementary reinforcement, we can neglect the last failure mode. And there are some limitations in terms of dimension of the fasteners in AS 5216 chapter 2. If fastener meets all these requirements, the fasteners can be designed according with concrete cone capacity method, which is given in chapter 6 for the tensile load in AS 5216. The important limitations here are in terms of depth and diameter. In terms of depth, for the chemical anchors, it has to be greater than 40 mil and less than 20 times the diameter of the rebar. If all these requirements are met, we design using concrete cone capacity method, no matter whether there is reinforcement as a anchoring element or threaded rod as an anchoring element. And we call this design philosophy as anchor model in this presentation. So I will be referring to anchor model again and again in this presentation. The anchor model refers to concrete cone capacity method. I'm not going into the detail of the concrete capacity design method in this presentation. This method is already there from SATS 101 to AS 5216 2018 version. This is the one very important failure mode I want to talk about, which is a pull-out failure. The equation you can see in the screen is used to calculate the pull-out capacity of anchors. The NRKP on the left-hand side of the equation is the characteristics pull-out capacity for the fasteners or a group of fasteners, and that depends on N0 RKP. N0 RKP is the reference pull-out capacity, and this is modified by a whole lots of factors depending upon the site conditions. To calculate N0 RKP, we use this equation, and that depends on tau RK and the diameter of the fasteners and effective depth of the fasteners. If you look this equation more closely, this is the product of bond strength and the contact area of the fasteners and the surrounding chemical. That means it assumes that the bond strength tau RK is uniformly distributed throughout the length of the anchor. And we call this uniform bond stress model. And this uniform bond stress model is true for shallow embedment depth. It has been tested extensively for 8 to 10 times the diameter of the anchor, and it has been proved to work well if effective depth is less than 20 times the nominal diameter of the anchor. And this is the exact reason why there is a limit in the maximum embedment depth in the standard AS 5216. As you might expect, this uniform bond stress model does not apply to the anchor with deep embedment. For the deep embedded anchors, the stress varies with depth, or it decreases as you go deeper. So we cannot use the anchor model from AS 5216 to calculate the pull-out capacity for deep embedded anchors or the deep post-installed reinforcing bars. Now let's come back to the possible failure modes for the anchor with deep embedments. So we have already ruled out concrete blowout failure and supplementary reinforcement failure if there are not any. And for the deep embedded anchors, concrete related failure mode, concrete cone failure is not possible either due to compressive stress of the concrete or due to the large embedment or some slab or splicing. So concrete cone failure and combined concrete cone and pull-out failure is not possible for the deep embedded anchors. Pull-out failure is possible, but concrete cone capacity method would not be applicable to calculate the pull-out capacity because the uniform stress distribution model is not applicable here. So the remaining failure mode is steel failure, pull-out failure, and concrete splitting failure. Concrete splitting failure is very brittle failure. So if we are designing especially for seismic application, we do not want this kind of failure. and most preferred failure mode for the post-installed reinforcing bar or deep embedded anchors would be steel failure. And for the steel failure, we need to design for the embedment depth so that steel failure happens. So if we are designing for the embedment depth to yield the reinforcement or to yield the bar, we could use AX3600. We don't know, let's see. So this equation, the equation given in AS3600, the development length equation, they are derived for cast in rebars. They are not for post-install reinforcing bar. The presence of extra layer of chemical between the reinforcement bar and concrete could alter the performance of the system. Also, the overall behavior of the connection depends on the chemical, its strength and stiffness. Again, here I want to make a note here. There is a provision in AS3600 for the epoxy coated reinforcement bar. This is not applicable here. Epoxy coating is different than having a thick layer of chemical around the rebar. So if in some way we can prove that post-install reinforcing bar works at least similar or better than cast in rebar, we can use the principle from AS3600 to design the post-install reinforcing bar connection. In other words, to use the principle from AS3600, we need some proof that the post-install reinforcing bars works at least similar to cast in rebar in terms of load transfer as well as load displacement behavior. And to compare the performance, we have an European assessment document EAD 330087. And this assessment document is now referenced in AS 5216. So what does this EAD do? So if you have a post-install rebar system that has a pre-qualification report in accordance with this EAD, it has been proved that the post-install reinforcing bar system works at least similar or better than cast in rebar. It is very important to note here that even if it is proved that the post-install reinforcing bar work better than cast in rebar, we cannot utilize the better performance of post-install reinforcing bar. In other words, if the bond strength of the post-install reinforcing bar is higher than that of cast in rebars, we will still have to use the bond strength of cast in rebar in the design. So I'll explain this with example in next few slides. Post-install reinforcing bar connection are designed for tensile load, and the verification is only done for tensile loads only. And as discussed before, the failure mode for the post-install reinforcing bar is assessed for steel failure, pull-out failure, and steel failure. Concrete cone failure is not possible for the deep embedded anchors. Okay, this is the overall process of getting ETA from the EAD. So this is kind of pass-fail criteria. To explain this, I took a screenshot from one of the table given in EAD, and it has 3 rows FCK. The first one is the nominal cylinder compressive strength of concrete. Second one, FBMREQ, is the required bond resistance for post-install reinforcing bar for assessment as equivalent to cast in rebar. And finally, FBDPIR is the design value of bond strength of a post-install reinforcing bar system. So this FBDPIR, the last row, is reported in pre-qualification reports such as ETA. So for the pre-qualification, they do a lot of experiment tests to calculate the bond strength of post-install reinforcing bar. And if the bond strength is higher than the middle row, or the FBMREQ, then we are allowed to use the bond strength of equivalent cast in rebar for that concrete strength. To understand this even more clearly, I use a 40 megapascal concrete as an example. So for the 40 megapascal concrete, the experimental value of bond strength is compared with 15.9. So if the bond strength from the experiment is greater than or equal to 15.9 for 40 megapascal concrete, the design bond strength of 3.7 can be used. So no matter how high the experimental bond strength, the design bond strength would be 3.7. So if you have a chemical with bond strength from the experiment, which is 16 megapascal or 50 megapascal, the design bond strength would be 3.7. Okay, so we cannot utilize the higher performance of chemical above equivalent casting system. And to design the anchors with this principle, we use chapter 13 of AS 3600. Once we prove that the system, post-installed rebar system, works at least similar or better than cast-in system, we use the design principle of cast-in rebar, which is given in chapter 13 of AS 3600 2018. And in this presentation, I am referring this design model as a rebar design model. There are two EADs for the pre-qualification of post-installed chemical anchors with reinforcing bar. The first one is the EAD 330499, and this EAD includes the pre-qualification of chemical anchors with threaded rod or reinforcing bar as anchoring element. This EAD, the EAD on the left, covers the rebar of up to 20 times the diameter of the anchor. On the EAD, on your right-hand side of the screen, is for the assessment document for rebar model. This EAD covers the pre-qualification requirement for rebar with effective depth greater than 20 times the diameter of the reinforcement. And this new EAD is now referenced in 2021 edition of AS 5216. If EADs are different, the pre-qualification report, such as ETA, issued in accordance with EADs are different as well. So the first one is the first ETA on your left is the ETA obtained from anchor EAD, EAD 330499, and the ETA on your right-hand side is for the ETA for rebar application, that is applicable for effective depth greater than 20 times the diameter of the rebar. The EAD number, the basis of the ETA, should be mentioned in the ETA itself. I have highlighted them with the red color on the left screen and the right color, green color on the right of the screen. So if the ETA is issued based on EAD 330087, we can use that for rebar model. And if the ETA is issued based on EAD 330499, we can use that ETA for anchor model. So it is very important to look at the basis of ETA number. To give some examples in the difference between these two ETAs, I have given the screenshot of one of the design table given in those ETAs. The normal ETA for shallow embedment anchor on your left provides the characteristics bond strength tau RK, and it is used for the calculation of pull-out resistance from the uniform stress distribution principle. Whereas on your right-hand side, the rebar ETA issued based on the rebar EAD is used to get the design value of ultimate bond strength FBDPIR. These two ETAs are for same chemical but for different application. As you might have noticed, these FBDPIR on your right-hand side are significantly smaller than tau RK. Let's look at one example. So I have highlighted the bond strength for M10 anchors for 20 megapascal concrete. So if you are using anchor model, the bond strength of 20 megapascal can be used to calculate the pull-out capacity in anchor model. In rebar model, FBDPIR is limited to 2.3 megapascal. So the difference is very large, almost 10 times. In the post-install reinforcing bar application, the actual strength of the chemicals are not utilized, but they are limited to the bond strength of cast-in reinforcing bars. Now I would like to briefly talk about the pre-qualification test and assessed parameter in EAD 330087. This is Rebar EAD. During the pre-qualification test, not only the mechanical resistance of the fasteners are assessed, but also the stability of the fasteners under different variables are also assessed. There are some optional tests that manufacturer or the supplier could request, such as fire test performance under a high temperature. Let me show you quickly what are the tests actually involved in getting the EAD. So in order to get an ETA approval or any pre-qualification report for the chemical, it has to pass through the several series of tests to be qualified for fit for purpose for that applications. So this is the screenshot from the EAD, appendix B of that EAD, and there are 18 series of tests that needs to be done before issuing ETA or the pre-qualification report. Some of them are optional, but most of them are compulsory. As you can see on your left side of the screen, these are the tests to calculate the mechanical resistance of the fasteners, the tensile test to get the FBD PIR. On your right hand side, there are some robustness or functioning tests. They check the robustness under different concrete conditions. They check different environmental conditions, different loading conditions such as sustained loading and so on. Finally, there are some optional tests for the extreme conditions such as fire exposure test. Again, they are optional and the manufacturer may request to do the test. After talking about the pre-qualification, let's briefly look at the design requirements in AS 5216-2021. There is a new appendix added to the standard. Appendix D of this standard covers the design of post-installed reinforcing bar connections where embedment depth is greater than 20 dB. Excuse me. The design method given in AS 5216-2021 is only applicable to the post-installed reinforcing bar which are pre-qualified in accordance with Appendix A of that standard. And Appendix A refers to EAD 330087 for post-installed reinforcing bar. And the design method in AS 5216 covers straight deform bar with diameter greater than 10 millimeter and concrete strength greater than 20 megapascal. The static and quasi-static loadings are covered in dry and wet concrete, and the post-install reinforcing bar connection should only be used in the intended application range specified in the ETA. The intended application range is also specified in EAD itself, but there could be some further limitations of the chemical in ETA. So this needs to be checked before using that chemical for that particular applications. These are some of the application examples covered in EAD. There are a few more, and I picked just 4 of them in this slide. In all these applications, the concrete cone failure is avoided. For the first figure, the concrete cone failure is avoided by this compressive force. In the splicing in the second and third figure, the tensile load is transferred from one rebar to another rebar by concrete compression struts, which prevent concrete cone failure. For the last one, simply supported beam, the concrete cone failure is avoided by compression struts if you follow strut and tie model for the analysis. So in summary, there are 4 major differences between anchor model and rebar models which a design engineer must take into consideration. And those 4 differences are: the first one, the load transfer, the type of load the fasteners is designed. In the case of anchor theory, the anchor can be subjected to tension and shear or combination of tension and shear action. The shear is also taken up by anchor. On the other hand, in the rebar theory, the rebar can be subjected to tensile load only, and the shear is transferred from the existing concrete to the new concrete through the rough interface. So in the rebar theory, the roughness of the contact surface is very important. Second differences is on the assumption. The anchor theory assumes the uniform stress distribution model, as I mentioned before, to calculate pull-out resistance. Whereas the rebar application, it uses AS3600 principle and it assumes the non-uniform distribution of shear, so the bond stress. And the third and very important difference here is the possibility of formation of concrete cone. In anchor model, there is a possibility of formation of concrete cone or concrete related failure is acceptable, whereas in the rebar model, concrete related failure is not possible and they are avoided by different means, either embedment depth, longer embedment depth, or some compression around the anchor. The last differences is the presence of pre-stressing force from tightening the anchor bolts in order to clamp down the base plate, which is only typical to anchorage application, not in a rebar application. Based on those differences, the appropriate design method could be selected. So I have highlighted 4 guidelines to select the proper design method in this slide. The first one is whether there is a possibility of formation of concrete cone. If yes, then rebar model cannot be used. So we have to use anchor design model. And another one is in terms of embedment depth. If the embedment depth is less than or equal to 20 times the diameter of the bar, we can use anchor design model. And if it's more than 20 dB, we cannot use anchor design model. We have to use a rebar design method. And the requirement of shear load transfer from the fasteners, if yes, anchor design method should be used. We have chapter 7 in the standard to design for the shear loading. If there is no requirement, we can use a rebar design method. Finally, the base plate. Usually we don't need base plate for the rebar design model because we connect concrete to concrete without using any fixer plate or base plate there. If you need pre-tension force or if you need fixer plate to connect the element, it is recommended to use anchor design theory. And final topics I want to cover before I conclude my presentation is on the performance of post-installed rebar in cracked concrete. Crack may have a significant influence on anchors. So we have seen the decrease in anchorage capacity for the cracked concrete is 30% or even more in some cases. Whereas the rebar, the effect of crack is not that significant. Why? Because there is a difference in the orientation of crack in terms of anchor itself. In the anchor theory, the crack would be parallel to the anchors, thus the crack would significantly decrease the load capacity of the anchor. In the post-installed rebar connections, the crack are perpendicular to the post-installed rebar, thus the crack does not affect the bond strength of the rebar, and the differentiation between cracked and uncracked is not that significant in most of the time. So I'd like to finish my presentation with this familiar slide. Jesse already talked about this slide at the beginning. So the very important one, 3 critical elements to achieve quality assurance. The first element is the pre-qualification. The pre-qualification is done in accordance with Appendix A, and Appendix A refers to EAD 330087. The objective of this EAD or Appendix A is to ensure that post-installed reinforcing bar performs at least similar or better than cast in rebar. The performance should be compared in terms of strength and displacement behavior. The second one is the design. The design of post-install reinforcing bar is now covered in AS 5216-2016 in Appendix D. So the concrete cone capacity does not apply, and we use a rebar model to design a post-install rebar connection. And finally, the installation is very important. Installation in accordance with manufacturer installation instruction is very, very important. For post-install rebar connection, the required hole depth may be very large compared to chemical anchors, and hence the installation quality is extremely important. The installation must be carried out in accordance with the manufacturer's installation instruction. The installation should only be performed by competent personnel. We recommend that the installer should be trained to install such anchors either by AEFAC or trained by anchor supplier for this specific application. Thank you. Now I'd hand over to Jesse for another topic.
So I'll now take over and discuss about fastenings for redundant non-structural systems. My name is Jessie. I'm a senior lecturer at Swinburne and also the training and development manager at AEFAC, where I mostly look after the AEFAC installer certification program. Now, fasteners for non-structural redundant systems, they are commonly seen supporting cable trays, air conditioning ducts, pipes. And I guess the main difference between what we call non-structural redundant fasteners and single-use fastener or single-use anchors is explained in this slide, where for single-use fastener, the failure of the single anchor will result in a system failure, whereas for a redundant fastener, sometimes the European might call it a multiple-use fastener. The term multiple use might be a bit misleading because it does not mean that the anchor can be used multiple times. It just means that the anchor system, the system has redundancy. So for redundant fasteners, the failure of one fastener will not result in a system failure. The system is basically a statically indeterminate structure where load redistribution will occur when one fastener fails. Load will be redistributed to the adjacent neighbors. So it is a statically indeterminate structure. So for single-use anchors, they are designed according to sections 6 and 7 in AS 5216, whilst for redundant fastening, design is done according to Appendix E in AS 5216. So the redundant fastening has less stringent pre-qualification requirements compared to their statically determinate counterparts. They have the same range of probability of failure as the single-use fasteners, which is 1 in a million. The redundancy is achieved via intentionally over-specification the number of anchors. The attachment should be sufficiently stiff to have effective load redistribution from one anchor to the other should failure occur. Hence, the allowable bending stress and deflection of the attachment should be limited. So the scope in AS 5216 under Appendix E covers for post-installed mechanical and chemical fasteners. So this can be your concrete screw anchors, the torque control expansion anchors, drop-in anchors, and bonded fasteners. AS 5216 only covers for safety critical applications. So Appendix E only applies for non-structural redundant fastenings for use in safety critical applications. There is a requirement of minimum 3 fixing points. As you can see in this diagram here, these are the number of fixing points available for this system. So there needs to be a minimum of 3 fixing points in order for it to be a redundant system. Because if you only have 2, then failure of one may result in the system failure. Right. And all fasteners in a fixing point must be the same. So once again here, this fixing point has 4 fasteners, and all of the fasteners in that fixing point must be exactly the same. So if you're using a particular type of concrete screws, they need to be all the same size, same brand, same embedment depth. And once again, the non-structural system needs to have sufficient strength and stiffness in order for load redistribution to occur without impairing on the functionality during serviceability or ultimate limit states. So non-structural redundant fastening anchors are pre-qualified according to EAD 330747, which is referenced in Appendix A. This covers for a working life of 50 years. The minimum diameter of fasteners pre-qualified is 5 mm with a minimum effective embedment depth of 30 mm. They can be pre-qualified for use in normal concrete and precast pre-stressed hollow core slab. So the minimum thickness of this, if you refer to the EAD, is 80 mil for normal concrete and a minimum wall thickness of 17 mil for the hollow core. The pre-qualification covers for only static and quasi-static loading. Hence, it does not cover seismic, fatigue, or impact. The redundant fasteners can be used in uncracked or cracked concrete, and the pre-qualification will give the characteristic resistance for tension and shear loads. Fire resistance is covered for mechanical fasteners only in the pre-qualification. In terms of the design, load calculation wise, all fasteners are assumed to be effective in carrying load. The design load is limited to the fixing point. So if you only have 3 fixing points available, then the maximum design load on each of the fixing point would be 2 kilonewton. For example, this diagram here, we have 5 fixing points. Hence, each fixing point is limited to 3 kilonewton. Now, if one were to do the analysis and found that the load on a fixing point is greater than 3 kilonewton, in order to use the redundant non-structural system, one would need to increase the number of fixing points in order to bring the load down. If this is not possible, then a single-use fastener will need to be used for the design. So to conclude, again, let's look at our quality assurance framework. So for non-structural fastenings, the pre-qualification is done according to EAD 330747 as referenced in Appendix A. Design is done according to Appendix E. And again, all post-installed fasteners will not perform properly if they are not installed properly. Hence, the installers need to have adequate competency to install these fasteners. That's all from me. Thank you very much for your attendance.